thank you for letting me speak here. And it's nice work here. Okay, so this is a joint work with several people. So Antoine Neal, part of this was his master's project, which he did before the pandemic started. And then also with colleagues in France, Arnaud de Massenet and Maurice Long. So I want to talk about unique games problem. So this is a well-known conjecture, the unique games conjecture, but it's an optimization problem.
Alantha, can you try to speak a bit louder?
Okay. So it's an optimization problem. Is this good? Okay. So we're given a graph, and every all the variables. There's a variable for every vertex, and for every edge there's a constraint. And the general problem is that we're given a permutation. We want to assign the vertices labeled 0 to a q, for integers 0, 1, 2, 3, up to q minus 1. And for every edge, there's a matching between the labels for u and for v. And this matching can be, perfect matching can be different for every edge. That's the general problem definition. And the goal is you want to find a label in the vertices so you maximize the number of satisfied. And the unique game conjecture is roughly that there's no efficient approximation algorithm that is a constant factor that's independent of q. So you fix some large enough q, and then if you fix any constant, like I say, I claim I have a 1/10th approximation, but then the adversary finds some big instance with some large q, some family of instances, and I cannot find a 1/10th approximation on this family. That's the conjecture, that you cannot approximate this with any constant. So there was some recent progress. So another way to state this is you cannot distinguish between 1 minus epsilon and epsilon in satisfiable instances. So they proved that they cannot distinguish between 1/2 and epsilon, but it should be easier to distinguish between very satisfiable instances, which is 1 minus epsilon and epsilon. Okay, so this is just some background, and there's a sub-exponential algorithm. So here we want this, for this talk, we will focus on a special case, which is linear equations by Q. So here we have the same problem, except for every edge we have a specific permutation, and it's a shift invariant permutation. The goal again is to find the maximum number of satisfied constraints. And this is in fact equivalent to unique games. You can just focus on this easier question. This was shown by these authors. And again, so the conjecture is that there's no constant factor for this problem. So to explain clearly, we have an instance, for example, here's an example of an equation. We have xj minus xi equals 4. So one thing to notice is, and q here is going to be 16, is that there's always q solutions, right? So that's why it's shift invariant. So for any solution that you have, you can always have, if xi is equal to 0, there's another solution with xi equal 1, xi equal 2. You just shift the solution. So you can think of this as a cyclic ordering problem where you have these directed distance constraints. So every constraint is explicitly saying what the distance is. So if xi is 0, then xj has to be 4. If xi is 1, then xj has to be 5. So it's exactly a directed distance on the circle. And for every constraint, if you take the opposite order of the variables, then you get a q minus the cu. So the equivalent constraint. So it doesn't matter which one you pick, you can arbitrarily order the edges and direct the edges. This is your set constraint. Okay. So a random algorithm gives 1 over q. There's 1 over q approximation. And this is the best in general. You have these factors that are still a function of q. So in general, the applications of this problem, of course, is for the unique games conjecture. You have, if it's true, it implies a tight inapproximability result for these standard, a well-known optimization problems like vertex cover and maximum cyclic subgraph and max cut. And then also there's a lot of work on trying to find, identify classes of graphs that are hard. So coming up with algorithms to show the class is actually easy, or identify a hard instance of the problem. So that's in order to prove hardness. So there's also another practical application of this of a problem that's very similar to games. To linear equations by Q, and it's called angular synchronization. And in this problem, we're given a set of angles, differences of angles, and you perturb each angle a little bit. And you know you're given a satisfiable instance of these angles, and you perturb each angle a little bit, and you know the distribution of the random noise usually. And then you want to find the original set of angles. So it's not completely constraint satisfaction because you're trying to recover the ground truth. But there is papers in this same community where they look at something that's much closer to unique gain. So for example, the model that they have is they fix a satisfiable instance or a set of angles, and then they with some probability the angle is good. So you actually give the offset that's correct, the accurate offset between the two angles. And then with some probability you just give a uniform chosen angle offset. And this is this problem is studied on complete graphs. And the original problem is also there's lots of papers on complete graphs as well, although normally it's not studied on complete graphs. There are instances where it's studied on complete graphs. And they're general, there's no analysis for the worst case. So the worst case would be that the angles would be chosen, the edges that you're going to perturb are chosen adversarially, and the actual perturbation chosen adversarially. But that's not the case in these models, but that's a valid question. And the Q here is really just the discretization of the angle. For example, in this paper by Singer, they use like 2 decimal points of precision. So it's kind of like Q is 100 in their problem. Okay, so that motivates this problem on unique games, for complete graph, if you didn't find any work in the literature. So this is a problem we have to look at now. So just to recap, we have this complete graph, and we have a variable for every vertex, and we have this linear equation on every edge. And now we want to minimize the number of unsatisfied constraints. So this is so let's say actually from this paper by Singer, with even the uniform perturbations, it seems like it's probably not a very hard problem. So we want to look at the kind of the hardest version, which would be minimizing the unsatisfied constraints. And another motivation is that there are these problems like feedback Arcset interminants or correlation clustering and complete graph, where they've been well studied on complete graphs, and tournaments of a complete graph, and they actually have very different algorithms from the general case. So it's interesting. For example, of course, if you have something like max cut, then on a complete graph, it's not very interesting because it's just one answer. But some of these problems stay on hard and complete graphs when they are interesting. And a priori, it's not clear if this problem is on hard or not. So what is known for this problem in literature is that if G is an expander, then there's a constant factor approximation for the maximization problem, and of course a complete graph is an expander. And there's also some other work that imply constant factor approximations using the SPP hierarchies. And there's also p-task, but the p-task, the Q and the 1 over epsilon are in the exponent, so they're not.
You shifted from the maximizing satisfied constraints to minimizing unsatisfied in all the bullets in this slide.
Yes, all these results are, okay. So, they studied G when G is an expander. I'm just saying that they looked at the maximization problem. The other results are for the minimization problem, okay? And the feedback Arcset and correlation clustering on complete graphs are minimization versions of the problem. So yeah, everything here is minimization.
So for example, for the max cut, even on a complete graph, it's not that easy because CUV could be 1 or 0. So
but a max cut it's always 1, not 2. It's actually
okay. So that's what what you by okay, good.
Right. But linear equations mod 2, when you're allowed to have 0 or 1, this is exactly correlation clustering in complete graphs with 2 clusters. And this had a p-task by it's great. Yes. So what we want to look for is what's called a robust approximation algorithm. So the robust approximation algorithm is when you have, for any instance, is 1 minus epsilon satisfiable. You want to find an assignment that's 1 minus f of epsilon satisfiable. And your loss function has to be just a function of epsilon, and it has to go to 0 as epsilon goes to 0, and the runtime can't depend on epsilon. Can't be 1 over epsilon, n to the 1 over epsilon. So for example, if f of epsilon is square root of epsilon, which it is for next general graph, and the runtime is n squared, then that will be a robust approximation. Okay. So for our problem, this is, the f of epsilon loss function is the approximation for the minimization version. Okay. So for our problem, we give an approximation ratio algorithm with loss function, which is epsilon plus some constant times epsilon squared. But here, epsilon is, I give you the instance, and epsilon is the opt. So, epsilon m, that's the size of the opt. So it's just one epsilon that you're finding, but not like a two-tens. And here, so this constant is a function of epsilon, but it has a limit. So it's at most, say, 16. And this epsilon squared is like much smaller than epsilon, because epsilon is less than 1. So you kind of approach epsilon, you kind of approach opt, but it's still incomplete. Okay, so the algorithms or the techniques that are known for linear equations of mod p, in general, are you take for example, if you have a spanning tree, it's an easy instance, you just propagate the value on a tree. Or if it's all satisfiable, then it's easy, which is equivalent to having, say, no inconsistent cycles. So let me just give an example of an inconsistent cycle. So you have a triangle, and the triangle is u, v, w. Okay. And you have, say, x, u minus x, v is equivalent to 1 mod 3, and then you have x, v minus x, w is equivalent to 0 mod 3, and you have x, w minus x, u is equivalent to 0 mod 3. And obviously, you can not satisfy all of these constraints. So but you can always satisfy 2 of them, because 2 of them form a tree. Okay, so equivalent formulation for this is just finding a hidden set for all the inconsistent cycles. So it's like an implicit hidden set problem. And a lower bound is a fractional packing of inconsistent cycles. So for example, a fractional packing of triangles is a lower bound. And one possible algorithm is you could just find a random spanning tree and use this assignment.
When you say G and expanded, should I think of like a sparse expander or any?
Any expander.
So like including like complete graph or anything?
Yeah, like complete graph. But that's easy for the maximization problem. Okay. Actually, it's not clear what I mean by easy. Because, these are completely satisfiable, the first 3, and then maybe the second one shouldn't, the third one, the expander shouldn't be there anymore. But, yeah, it's a constant. So now we want to get an approximation for the complete graph. Okay.
So going forward, we're going to think about the minimization problem.
Yeah, we're minimization on complete graph. Okay. So we pick a pivot at random. And for each edge, you just assign the label according to the edge of that constraint. So without generality, the pivot can just have that label 0, and then every edge will just get that value, right? And then all those green edges on the top, they're satisfied because they have the correct value. But you could have some errors in between the points. And so this is actually a spanning tree algorithm. You're picking a spanning tree and satisfying spanning trees. And this gives you 3 approximations, actually exactly the same algorithm as these other problems of complete graphs, so it's not so surprising. And the common property is that they're all vertex labeling problems of complete graphs with fractional triangle or triangle pattern over them. It seems like probably if your problem is like this, then you're going to get 3 approximations. So the analysis is just that you have this, say, red edge, and this red edge is charged to some triangle T, which is inconsistent. And so if a triangle is chosen as an inconsistent triangle, one of its points is chosen as a pivot, then it contributes PT. That's the cost of the algorithm. But then you can show that PT over 3 as a packing. It's just because for every edge, you have some edge, and you look at the triangle, you look at all the triangles that use this edge, and so if this edge E is chosen, then this triangle is chosen, and then one of the vertices is chosen as a pivot. But this can happen exactly with probability PT over 3, and that's true for each of the triangles it belongs to. And therefore, only one of these events happens, so it's a probability. It's a pattern. Okay, so this analysis is actually tight, like it is for all the other problems that you can use this algorithm for. And maybe you can do better. For example, we'd like to look at an SVP, the one that they use for the expanders. You can do better. So I have a SVP, but I'm not, this is just for explanation. So, here, this is the algorithm that they use for the expanders. So you have a constellation for every vertex. You have Q vectors, and you take the 2 constellations for each vertex, and you find a minimum cost matching. And that's a new permutation. And now you do the pivot algorithm in that permutation. That's their algorithm. That's what they do. But the thing is that here, there's no reason that the permutation you get back from an SVP would be different from the permutation you put in for the complete graph. So so it's not clear that you should get better than 3 with the Newman SVP, because it should be predicted the same permutation. So now we have this voting algorithm. So what we do is we try to improve the algorithm, the output of the pivot algorithm. We take a pivot, and then you give it a temporary value, a vote, and then for every vertex, say for example this vertex here, you look at all the votes, all the vertices. All the other vertices have a value, and look at a constraint that's connecting that vertex to the one you're trying to find the new value for, and they have they each have a value that they want to assign that vertex, right? For example, the first guy gets a 0, and then let's say the constraint on that green edge is that they should just be 0, and maybe the constraint on this edge is that they should be 1. So then he would give this vertex, he would vote for 1. So there could be 2 possible coalitions, and you take the biggest one. You can break ties arbitrarily. Okay, so this doesn't have anything to do with epsilon on this okay, so to explain the main ideas of the analysis, we want to say, so we say a vertex is flipped if it's different from the optimal. Okay. But if it was equal to the optimal, then it would be the optimal, and if it's different from the optimal, it could possibly create new unsatisfied edges. So if a vertex is not flippable, if it's incident to a sufficient number of green edges, because if it's adjacent to all these incidents, all these green edges, only epsilon fraction of them could have the incorrect vote from P, the incorrect value from P. So all the edges that are on green paths, which are going to be voting for the correct optimal value for B. And so if you have a certain number of green edges, then you will definitely vote correctly. That's the point. If you have a few, so in order to vote incorrectly, you need to have a sufficient number of red edges. Red edges, I fix an optimal solution, and the green edges are the satisfied edges in that optimal solution, the green are the unsatisfied edges in that optimal solution. So I need to have a certain amount of red edges in order to be voting correctly, but there's a finite number, there are not that many red edges, and only epsilon m of them, and they can only contribute to 2 vertices. So that means that there's not very many of these flippable vertices. So if you just, and there's approximately 2 epsilon n of these flippable vertices. So the flippable vertices, if you just say if they form an independent set and all the edges around them are unsatisfied, then this is sort of like a 4 approximation. But in fact, you can show that if this coalition actually votes, then what happens is that the red edges that are unsatisfied in the optimal solution, if they actually, a large set of them vote to change the value of V, they actually become satisfied. So around the flippable vertices, you actually have a lot of satisfied edges. So, okay, I won't go into the details, but in the end, if you do some, so the point is you have some charging schemes. Your actual number of unsatisfied edges at the end is the optimal is epsilon m plus the total charges times number of these flippable vertices. And the charges are ones that get flipped to red, they become unsatisfied, that's a positive charge. And if they're red to green, they become satisfied. So you just want to know the opt plus the total number of charge. And you can show that this is approximately some constant times epsilon squared m plus the original number of unsatisfied edges. So the next thing I just wanted to say is that another way of looking at this algorithm is just to take, so you start out with your complete graph G, and then you make another graph G prime. And for every edge in G prime, you look at G, I mean you look at G, look at some edge E, and you look at all the paths in E. There's n minus 2 of them. And they, these constraints imply a single constraint. So you have n minus 2 constraints, and then you vote and you assign this guy a new constraint. You got some new constraint, G prime. I mean, but this is what happens in G prime. So G prime is always as these new constraints you get when you voted. And now you just run the pivot algorithm on G prime. This is exactly our algorithm. This is no way to do. But I don't know how to analyze that using a rule. So yeah, you can also show this is empty hard, not quite, but it's under randomized reductions because the reduction is also almost exactly the same as feedback Arcset interments, except that you need this gadget. You can only prove the gadget exists, but we can't find the gadget. So it's not exactly empty hard. It's under the assumption that empty is not an empty. So some open problems. So one question I think is interesting is, so for example, maybe feedback Arcset interments actually has a really good approximation like this. I don't know. It has a p-test, so there's no reason why it couldn't, but the p-test of course is running, the runtime is not polynomial. And even if you can get a better constant, so the best constant for feedback Arcset interments is, well, there is a p-test, but like if you're only allowing polynomial time, it's 2.5. Maybe you could get something better if you restrict your running time. Okay, thank you.